Hello, my friends, and welcome back to Survival Roots. If you care about building smarter, choosing practical materials, cutting waste, and creating a home or homestead that stays useful when expensive systems fail, then this video is for you. For years, we've been told that solar power has to mean costly silicon panels, complicated inverters, and sealed systems the average person can't build, repair, or truly control. But from a builder's point of view, that story never made much sense. Because what if the better tool is not a fragile piece of electronics, but a simple reflective surface shaped with purpose? What if the strongest low-cost energy system for real-world self-reliance is something you can understand, assemble, maintain, and afford without handing your future over to a utility company or a pile of proprietary parts? While standard PV panels often turn only a small share of sunlight into usable electricity, there is an older method that captures the sun as heat with far greater efficiency using basic materials like reflective film, pipe, water, and geometry. In this video, we're going to uncover that forgotten approach and answer one big question. Why are PV solar panels such a weak fit for true independence? And what can you build for around $100 instead? If you're into practical building knowledge, honest material choices, and budget-friendly survival systems, subscribe to Survival Roots. And let's get into it. Part 1. The Great Solar Deception. Now, before we get to the better system, we need to be honest about the one most people have been told to trust. Standard photovoltaic, or PV, panels may look modern and impressive. But when you study them from a practical building standpoint, the weaknesses are hard to ignore. The physics alone tells a disappointing story. A conventional solar panel depends on the photovoltaic effect, and that process can only convert a limited portion of sunlight into electricity. The rest, most of it, is lost as heat. And here is where the problem gets worse, not better, because that trapped heat does not just go to waste. It actually drags panel performance down even more as temperatures rise. But poor efficiency is only part of the issue. The real-world cost of PV begins long before a panel reaches your roof. These systems depend on a massive industrial chain of mining, refining, global shipping, high-energy manufacturing, and specialized electronic components. And at the end of that life cycle, what are we left with? Millions of tons of aging panels that are difficult and expensive to separate, process, and truly recycle. A lot of what people call recycling is really just downcycling into low-value filler material. Then there is the issue that matters most to anyone serious about resilience: control. PV systems still push you back toward inverters, software, service contracts, and utility rules that keep a middleman between you and the sun. If one critical component fails, or the company behind it disappears, that expensive setup can become little more than dead weight on your roof. And when a system is too complex to repair with your own hands, that is not independence. That is dependency dressed up as progress. Part 2. The Forgotten Pioneers. So, how did we end up here? How did a technology that should have moved us toward true self-reliance become so expensive, fragile, and controlled? To answer that, we have to step back to a time before modern households were locked into centralized electrical systems, and look at the people who understood solar power in a very different way. In 1866, a French mathematician named Augustin Mouchot built a large conical mirror that focused sunlight onto a boiler protected by glass. This was not a weak experiment or a novelty machine. It generated enough steam to run mechanical equipment and even produce ice, proving that the heat of the sun could do serious industrial work. Decades later, in 1913, Frank Schumann pushed the same idea even further in Egypt. Using enormous parabolic troughs stretching over 200 feet, he built the first large-scale solar irrigation system and pumped thousands of gallons of water per minute with nothing but concentrated sunlight. That was a clear demonstration that glass, metal, and smart design could deliver real power without fuel deliveries or utility dependence. And around that same era, George Cove developed a solar electric generator that achieved impressive results with remarkably simple materials. His design used zinc and antimony in a way that captured both visible light and shortwave infrared heat. And unlike many modern systems, it did not depend on toxic layered protection that becomes difficult to recover later. So why do people rarely hear these names today? It was not because their ideas failed, it was because history took a different turn. War, cheap oil, and the rise of centralized energy markets pushed practical solar innovation out of the spotlight. Oil could be extracted, shipped, sold, taxed, and controlled. Sunlight could not. And that is exactly why these early breakthroughs matter so much as we move into the next part. Part 3. The Power of Geometry. And this is where the real advantage begins to reveal itself. The reason a parabolic thermal system can outperform a modern silicon panel comes down to one basic difference: chemistry versus concentration. A flat PV panel tries to convert sunlight through a limited electronic process. But a parabolic reflector does something far more direct. It gathers light, concentrates it, and puts that energy exactly where you want it. The shape is everything. When sunlight hits a flat surface, it spreads back out in a broad direction. But when that same light strikes a properly formed parabolic curve, the reflected rays are redirected toward one narrow focal line. That means you are no longer just collecting sunlight across a wide surface. You are compressing its power into a much smaller space, multiplying the heat intensity again and again. Now place a pipe filled with water or oil right at that focal line, and you create an extremely effective thermal collector. Add a glass vacuum tube around that pipe, and the system becomes even stronger by letting solar heat in while sharply reducing heat loss. With that simple combination of reflective material, shaped structure, and a properly placed receiver, temperatures can climb well beyond 392 to 572 degrees Fahrenheit. At that point, the fluid inside is no longer just getting warm. It is changing state, producing high-pressure steam. And that is the moment when a simple pipe stops being plumbing and starts acting like a real power system. Part 4. The $100 DIY build. Now I know what some of you are thinking. This sounds powerful, but it also sounds expensive, technical, and far outside the reach of an ordinary homeowner or homesteader. The good news is that the basic design is far simpler than most people expect. You do not need an industrial factory to build a working solar trough. You need a practical layout, basic shop tools, and materials that are easy to source without destroying your budget. Instead of the heavy silvered glass used in commercial concentrating solar plants, a DIY version can use acrylic mirror sheets or aluminized mylar film with very strong reflectivity. For the frame, you can cut plywood ribs into a parabolic profile, build with PVC, or use other lightweight supports that hold the curve consistently. At the focal line, a standard copper tube painted matte black does an excellent job absorbing heat. It is simple, affordable, repairable, and exactly the kind of material a builder can trust. The key design rule is concentration ratio. A solid, small-scale trough should aim for at least 15:1. In simple terms, that means a wide, reflective surface is concentrating the sun onto a much smaller receiver pipe, forcing more usable heat into less space. The biggest challenge is not the materials, it is keeping the reflector aligned with the sun as it moves. But even that does not require expensive tracking hardware. A pair of photoresistors and a slow motor can do the job. Or, if you want something even simpler, you can orient the trough on an east-west axis and make seasonal adjustments by hand. You lose a bit of efficiency, but you gain simplicity, lower cost, and fewer parts to fail. Part 5. The ultimate heat battery. But a good system is not just about collecting heat. It is also about keeping that heat when the sky goes dark. And this is where thermal design pulls even farther ahead. One of the biggest weaknesses of conventional solar setups is that they push people toward lithium-ion batteries that are expensive, chemically sensitive, and limited by cycle life. That may be acceptable for some electrical uses, but it is a poor answer for people whose real daily needs are hot water, warm rooms, and reliable cooking heat. Here is the practical truth. Using electricity just to make heat is an inefficient detour. Yet that is exactly what many homes do. A parabolic trough avoids that waste by delivering boiling water or steam directly into storage designed for heat. That storage can be an insulated pressurized water tank, a sand battery, or a phase change material system, depending on budget and application. In every case, the idea is the same. Store heat as heat, not as electricity first. And from a building and cost standpoint, that makes enormous sense. Thermal storage is cheaper, simpler, and more durable than chemical storage. Well-designed heat batteries can reach round-trip efficiencies around 95%, and unlike lithium batteries, they do not steadily wear out after repeated cycling. A properly insulated system can hold most of its energy for more than a full day. That means strong sunlight on a bright afternoon can still give you floor heat, hot showers, or cooking steam the next morning, even when the weather turns. And when you look at the economics, that kind of direct, durable performance can shorten payback to just a few years, while bringing the cost of usable heat down to only a few cents per kilowatt hour. Part 6. The Plug-and-Play Solar Rebellion. Now maybe you are watching this and thinking, this all sounds great, but what if you do not have a backyard, a workshop, or the freedom to build a full parabolic trough? What if you live in an apartment, rent your space, or simply need a smaller first step? That is where the decentralization mindset opens another door. Enter plug-and-play solar. In places like Utah and Germany, more people are turning to compact systems built around microinverters and small balcony panel setups. These are not massive rooftop projects. In many cases, they are just 1 or 2 panels connected through simple equipment that can feed power directly through a standard household outlet. Because these systems stay under about 1,200 watts, they can often avoid the heavy permitting, contractor costs, and restrictions that come with larger, permanent installations. Compared with traditional rooftop solar, the cost can drop dramatically. But the real beauty is portability. If you move, your system moves with you. You are not leaving behind a costly installation tied to someone else's property. And that changes the equation completely, because utility control becomes much weaker when ordinary people can reduce consumption with simple, movable equipment that does not depend on a full-scale rooftop contract. It is another practical way to take some power back for yourself without asking permission to build something permanent. Part 7. Reclaiming our power. And that brings us to the deeper point behind all of this. The choice between an imported, failure-prone PV setup and a simple DIY solar thermal system is not just about engineering. It is about independence. It is about deciding whether your energy future will be controlled by distant supply chains and utility policies or by tools and materials you can understand with your own hands. When you build a parabolic trough, you are not just heating water, you are reclaiming the basic laws of energy in a form that is visible, mechanical, and repairable. There is no mystery box here. If a pipe leaks, you fix the pipe. If a bracket bends, you straighten it. If a motor stops, you troubleshoot it with tools instead of software licenses. That kind of system fits the real spirit of resilience far better than a sealed product that fails silently and leaves you dependent on outside support. And once you step away from the all-electric, grid-tied model, you begin stepping away from a much larger fragility. When you own the heat, you own something fundamental. You can cook, wash, warm your living space, and support basic mechanical work without waiting on the utility, the market, or the next shipment of specialized electronics. That shift matters. It turns energy from a metered service into a practical resource you harvest yourself. And more than that, it creates a different kind of culture, one built on self-reliance, shared knowledge, and community strength instead of permanent dependence. Conclusion. So, in the end, the parabolic solar trough is more than an interesting old idea. It is a bridge between the mechanical intelligence of the past and the survival needs of the present. It shows that one well-focused reflection of sunlight can offer more real-world security than years of chasing fragile, expensive battery-based solutions. Somewhere along the way, we traded high thermal performance for a lower efficiency system that was easier to package, sell, and control. But the knowledge itself never disappeared. The plans are still out there, the materials are still available, and the basic logic is still as powerful as ever. So now the question is simple. Are you ready to own your heat? If you believe practical building knowledge, affordable materials, and decentralized survival skills still matter, subscribe to Survival Roots, like this video, and share it so more people can find this knowledge before it disappears again. Stay resilient, stay independent, and I will see you in the next one. This is Survival Roots, signing off.